on this. All right. So anyway, I'll just add that slide later. Okay. So if we go to our sp hybridized, that's 50% s. One s, one p spread out over two bonds, 50% s. So the s orbital is smaller. The s orbital holds on to those electrons tighter and makes that hydrogen more acidic. Okay, so let's look at that hybridization. This is our sp3 hybridized, and it has a pKa of around 50. Okay, trying to pull that hydrogen off is very, very hard. It has 25%. Now let's go up, move it up to our sp2 hybridized. It has a pKa of around, let's see, I think it's 45, no, 40. And then if we go to the last one, this sp hybridized, the pK drops all the way down to 25. 25. Let me double check this number on my next slide here. Okay. 44, I was close, 44. Okay, so hybridization. First thing, electronegativity, if you're going along the same size. Second is size, if you're going down a row. Third is hybridization. So what we should see here is that the different types of hydrocarbons, you have different acidities. And those are three things you'll have to remember on our list of things to remember on our pKa's. Okay, does that make sense? Okay. All right, so let's go to our third thing, which is resonance. The more resonance structures you can have, the more acidic that hydrogen will be. The more you can spread that negative charge after it leaves over a number of atoms, the easier it will be to get it to leave. So the way we think about this is, the best way is to look at something like ethanol. Oops. Ethanol here, OH, okay? So we have an oxygen, we have a hydrogen, we know that that has an acidic bond, and this has a pKa of, let's see, I think it's 16. 16, okay. So if we were to pull this hydrogen off, all of this electron density is going to stay on this oxygen. So we're going to have O minus. It stays all on one atom, okay? But what if we had, instead of that, we had acetic acid instead, right here. And we know that if we were to pull off this hydrogen and these electrons would stay behind, our first resonance structure, and I'm going to put our lone pairs here, it's going to look like that. But because we can do the lone pair come in and this lone pair come out, we now have a second resonance structure, and we can spread that charge out. So because it's going back and forth in our resonance structure, we actually have partial negative charge on this oxygen, partial negative charge on this oxygen, and this can carry a little bit of that. So we're actually spreading a whole charge out over 3 atoms. Okay, so the pKa of acetic acid is 4.7. 4.7 right there. Has everything to do with delocalization. See how you cannot spread the charge out on this one, so it's less acidic. You can spread the charge out on this one, more acidic. All right, question on that. Okay, so if we have size and electronegativity as one of our factors, we have hybridization as our second factor, resonance is our third factor. Let's talk about inductive effects. This is the least influential on the system. So if we want to think about, of those 4 things we just talked about, what's most important? The electronegativity and size is going to give the biggest contributing factor to your acidity. The next thing that's going to do it is your hybridization. The next thing that's going to contribute is resonance. And then the last thing to contribute to it is these inductive effects. So just like before, when we were talking about all of our bonds, if we have a difference in electronegativity between two atoms, that bond's going to be polar, right? And there's going to be a partially positive side of that bond and a partially negative side of that bond. So what's going to happen is if you have an electronegative atom, it's going to be pulling electron density through that bond. It's inducing that. So it's an inductive effect. It's not directly bound to an atom. It's going through those bonds. So, so let's demonstrate that. So if we started out with something like acetic acid here, and we just put a CH3 on here, the carbon and hydrogen bonds here on the CH3 are not very polar, right? So we don't expect them to be influencing the acidity or not of the carboxylic acid right here. But if we were to take an electronegative atom, take one of those hydrogens off, and let's put a bromine there, right here. Our pKa, again, has not changed. It's still 4.7 here. Just by taking one of those hydrogens away and putting a very electronegative atom, notice the hydrogen's not on the bromine. We're not talking about the acidity of the bromine. We're talking about the effect of the bromine on the acidity. The pKa drops to 2.68. Just by having that bromine one bond away from this acid group. Now, and why do I say one bond away? Because, well, it's bound. Remember, this carbon right here, there's a resonance structure up here. So really, it's pulling the electron density from here to the bromine, giving us our increase in acidity. It has less of a full negative charge. And we can do it again with something even more electronegative. And we're going to do chlorine this time. Chlorine, and it has a pKa of 2.81. And you're like, but wait, hold it. When you said before, size and electronegativity matter. If the hydrogen is on that atom. Here we're doing an inductive effect. All we care about is electronegativity. So the fact that the chlorine is more electronegative than bromine, it increases the acidity more through that electron withdrawing effect. And if we do it again with fluorine, right here, the pK of that is 2.66. So in the inductive effect, it's all about electronegativity. In the size and electronegativity, it's about the combination of the two. So don't get those confused. Now, okay, so that's just changing which electronegative element is there. How does it affect it by proximity? If we were to take that electronegative element and move it from one bond away to two bonds away, is it going to have the same effect on the acidity? Probably not, because it can't draw as much. So let's pull that up there. And let's say we have slightly longer carboxylic acid here, something like that. And it's going to have a pKa of approximately the same as acetic acid, about 4.7. But if we were to put that bromine right here, it has that one bond difference between this, where it is pulling an electron density to this bromine. So it's only one carbon-carbon bond. And so this one has a pK of 2.97, okay? So we have the bond between the carbon and the bromine, and then the bond between the carbon and the carbon of the acid group. What if we move that bromine over one position to here? So instead of just being one bond away, it's now two carbon-carbon bonds away from there. And it has less of an effect because it can't pull as much through those two bonds as it could through the one bond. And so the pKa drops to 4.1, 4.01. And if we move it over one more here, the pK is going to drop again to 4.59. And if we move it a whole other one over, if we had another carbon there and moved it a whole one over, it's going to go back to 4.7 because it's so far away, the acid can't see it. Okay. So we understand the inductive effect. Okay, so those four things, and the inductive effect is the least influential, and it is least influential the further you get away. So proximity is important. All right, questions on that? Okay, so here's a summary. The first one is the element effect. And if you're just going down a row, down a column, down a row, it's all about electronegativity. If you're going down a column, it's all about size. Okay, so those are the two that how it affects it. The inductive effect is less of an effect. The further you get away, the less it has, because it has to pull through bonds. Resonance effect, how many atoms can stabilize that negative charge of your new conjugate base? And the last one is hybridization. Hybridization is particularly important for the carbon chains, especially the hydrocarbons. All right. Any questions on that? All right. So when we think about, really, really strong acids, we think about things that are, oh, sorry, skip the slide. Where's my slide? Oh, I might have, on the slide that's supposed to be here, I actually have pKa values to remember. But don't worry, it's also on Canvas. There is a new thing in resources called pKa slides to remember. So let me actually share this screen over here temporarily. Oh, I can't. All right. Let me see if it made it to this one. Wow, that slide is missing out of both of them. There it is. All right. So these are the pKa's you need to remember. The first and foremost is the carboxylic acids, which is the most acidic of our organic compounds. Okay. Those are the ones that are going to be right around 5. Okay. The next thing up is phenol. Phenol is an OH group on a benzene ring. Why would phenol be the next most acidic? Because the oxygen is next to the benzene ring, and it can use resonance delocalization around that ring. So that's why phenols are more acidic than other alcohols, because of that ring. The next thing we have is water and alcohol right at 15, 16. Okay, so you want to think of, they're weak acids, but they do have acidic protons. Now, the alkynes, alkenes, and alkanes, they change because of hybridization. So knowing that 25, 45, and 55, or 60, for those is important, okay? So devote these to memory because I'm going to use them a lot as we go through reactions. Okay, so I'm going to go ahead and get back to my other. All right, so now we're going to talk about the characteristics of strong organic bases. Okay, so we talked about pKa, right? And so the pKa tells us where the acidic protons are. And we found out if we had a very weak acid, it becomes a very strong base.
So there's on the slide above that. We passed them.
Oh, sorry. Yeah. Okay. Thank you. I missed that on there. Yeah, that's okay. It is there. Okay. So the most common acids, of course, from Gen Chem were things like HCl and HBr and stuff like that. And those are still strong acids. But when we talk about strong acids in organic, we talk mostly about things like acetic acid, or our carboxylic acids. And it's acidic because of the resonance, but we also have some other ones that are based on inorganic acids, OH, and then there's a methyl group here, right here. So this is like an organic version of sulfuric acid, and this is called para-toluene sulfonic acid. It's usually denoted as capital T, little s, OH. The reason it's OH is because you want to make sure you know it's an acid. So if we look at this, number one, we have a sulfur there, so it's already acidic, but we also have the resonance of that benzene ring. So it's very acidic material. In fact, this has a pKa of -7. This is around 5 pKa. So these are what we consider our two strongest organic acids that we'll use. And again, the other inorganic acids are all strong as well, except for HF. Remember, HF is just above 0. Okay. When we talk about bases, we want to think about, okay, let's take something that's very poorly acidic and pull a proton off it, and it's going to become a good base. So things like water, if we pulled the proton off it, we'd get hydroxide. So something like sodium hydroxide. But if we took an alcohol, like ethanol here, pulled this proton off, we actually end up getting what we call alkoxide or ethoxide. We've removed a proton from our, here, let me just draw it out. Actually. So we have O, and then CH2, CH3, and we have a negative charge on that. And remember, it has a very weak acid as the alcohol. It only has a pK of around 16, but that makes it a really, really strong base when we use it. Okay. And then we also have another very common base that we're going to use is if you take the T-butyl alcohol here and remove that proton, it becomes T-butoxide or tertiary butyl butoxide. We call that tert-butyl. And when we remove that proton, that also becomes a very, very strong base. Okay, so those are the oxygen-based organic bases we're going to deal with. Now we have a couple nitrogen-based ones too. We do this right here. This is called sodium amide, A-M-I-D-E, A-M-I-D-E. And it's a very strong, usually it has lithium with it. But you can take any nitrogen that has a hydrogen on it and remove it and make it a very strong base. This particular one is common. We'll use it more next semester, but it's called LDA, which is, it has a lithium as a counterion, and then it's diisopropyl amine. So it's LDA. And so that's a very strong nitrogen base, okay? Nitrogen bases are stronger than oxygen bases, which means the nitrogens, when we go look at our table, actually were weaker acids than the oxygens. Okay, and the last one I want to talk about here is this one here, hydrogen with a negative charge. Okay, it's called hydride. Okay, so if you think about it, hydrogen is your level 2, your level 1 here. It has 2 electrons to fill its shell. When it fills its shell, it has 2 electrons, and therefore it has a negative charge. Okay, it's a very strong base because of this. So we see hydrogen can have no electrons associated with it. It has a positive charge. Neutral, it'll have 1 electron. Sodium hydride is going to give us 2 electrons in that outer shell and makes it a very strong base. Now remember, our bases all have lone pairs, right? Our hydrogen now has a lone pair. So look at it, yes.
Did that hydride get an extra electron from the hetero with it?
It depends. It depends on how they make it.
Okay.
But most of the time, it's made through an inorganic reaction with metals. So what really happens is we start with lithium 0 and hydrogen as 0. And we actually remove an electron from the lithium to turn it into lithium +1 and hydrogen -1. So it's an inorganic process.
And are all organic bases just derivatives of like functional groups? So like we took a alcohol and took off a hydrogen and a base.
Yes, any place you remove a hydrogen, any acidic hydrogen that gets removed, your conjugate base is now a base and mostly strong.
So like amines, hydroxyl groups.
Correct, correct. And that's where they fit on the pKa scale. Okay, so thank you for not letting me skip those. So now we want to think about something a little different. Remember when we talked about pH, the pH scale went from 0 to 14, okay? But our pKa scale goes from like -9 to 50 or 60, okay? But the important thing about that 14 is that we actually can say that the difference in pKa between the conjugate acid, or between the acid and the conjugate acid, is going to be no more than 14. It's going to be exactly the same. Okay, so let's go ahead and think about our other organic bases. So strong bases have weak conjugate acids, right? So anything above 12 on our pH scale, on pKa scale, we're going to consider those very strong bases once they're deprotonated, okay? Now, because of that, when we look at our regular ones here, our regular acids, the conjugate base of HCl is chloride ion, right? Chloride ion is a very weak base. So we're going to see that it has a very weak base associated with it. And in fact, none of the halogens form strong bases at all. Fluoride would be the most basic because it has the highest pKa. Okay, now the one thing we really need to play with is what we call carbanions. So in the case of carbanion, just like a hydrogen with a negative charge, carbons, any carbon that has a negative charge on it is really, really, really basic. Okay, because if we think about just with a hydrocarbon like butane right here, we saw that butane, it has sp3 hybridization, so that means it's going to have a pKa of around 50 or 60. Okay, so its pKa is here. So if we remove that proton and generated an anion there, this is going to be super, super, super strong. Okay, so carbanions, negatively charged carbons, are going to be one of the strongest bases we use. Okay, and we'll use those when we talk about alcohols and conversion. Okay, so another common one that we have are the amines. The amines can be pretty decent bases here, and they are, just by itself, just the nitrogen. Let's say we have 3 ethyl groups hanging off this nitrogen, but we have this lone pair, right? That lone pair can act as a Lewis base. So that means our amines with that lone pair are basic, okay? So if we think about that, now they're not very strong bases unless they're negatively charged. That sodium amide or that nitrogen with a negative charge on it are stronger bases. But neutral amines also are bases used in organic chemistry. Okay, and so turns out that we can have something like, let's see, if we have butane right here, it has a pKa of, this acidic hydrogen is 50. Turns out when we have an amine like this, a trifunctional amine, and I'm just going to put R groups here because they can be anything. This has a pKa. Once we acidify it, have it positive charge here, pKa of 10. Remember, we only can do pKa's of acids, so we had the propane here of 10. So that amine is a much stronger acid as its conjugate acid, but it's a much weaker base than the negative charge on carbon. Okay. Okay. So what do we want to know about our carbanions, our strong carbon bases, and the solvents we can use them in? Okay. Okay, so let's do an equation here. Let's start with acetylene and put an acidic hydrogen on it. And we saw from our pKa chart that it's the pKa of this is 25. 25. And let's say we're going to use a strong base. And in this case, we're going to use sodium amide right here. And when it does that conversion, we ended up getting to H, a carbanion, the carbon negative there, plus NH3, the hydrogen is transferred. So this is our starting acid, and this is our conjugate acid. Okay. Does this reaction go forward? Well, how do we know that? You compare the acid on the one side of the equation to the acid on the other side of the equation. And in this case, it's the pKa of this conjugate acid. And this pKa is 38 pKa. So is 38 stronger than 25? Sorry. So it's weaker than 25. So that means that the acetylene is the stronger acid, which means the reaction is going to go to form the carbanion. Okay. What if we did this in something like carbon and, oh, let's do it with hydroxide instead. Okay. So if we draw the equation here, we have H with our carbanion, carbanion with a negative charge. And what would the conjugate acid of hydroxide be? We're going to transfer a proton, so it's going to turn it into water, right? So it'd be H2O, okay? And the pKa of H2O is 15. The pKa of the acetylene is still 25, which is the stronger acid? The water. So is this reaction going to go? No. Hydroxide is not a strong enough base to get the reaction to go. And the other thing to know about this is that anytime you have a solvent that has an acidic hydrogen on it, like water or alcohol, they're all going to react with carbanions. So you can't use those alcohols and water as a solvent in your system because the acid they create is too strong and the reaction won't go. Okay, questions on that? So that means when we form these very strong bases with these carbanions, we have to use solvents that won't react with them, like hydrocarbons and ethers. We can't use alcohols. We can't use water. We can't use anything. Can't use alcohols, can't use water. All right, questions? All right, so, why do we care about this water reaction? Well, it turns out we can actually use that water reaction to tell us where the hydrogen, which hydrogen got removed. And we can use this with a doping effect. I'm sorry, we can take a very strong base and expose it to a stronger acid. And if we did this, we'd end up with a hydrogen right there, right? Okay, what if we instead used a different isotope of hydrogen? We use one that's a little heavier. What if we used deuterium oxide? Okay. Ooh, that's cool because when we reacted that anion with deuterium oxide, we'd end up with a deuterium here. Okay. So by analyzing the difference between hydrogen and deuterium, we know exactly which carbon that hydrogen came off of by doing this label experiment. If we didn't know where the anion was, we could prove it here. And by using an even heavier isotope, tritium, we can also figure out exactly where that hydrogen goes. So that's one of the interesting things about using these radio labels is you can use it from a mechanistic standpoint to say, hey, exactly this hydrogen came off at exactly this place, and I can prove it because of this isotope labeling experiment. Okay, let's see. Questions on acids and bases. Okay. So acids and bases are really kind of important. Remember, Bronsted-Lowry acids and bases have acids and conjugate acids, bases and conjugate bases. That's very important. But you can also use the definition of a Lewis acid and Lewis base extensively in organic chemistry. A Lewis base is electron pair donor, usually has a negative charge or a lone pair. A Lewis acid is electron pair acceptor. Okay, so look for that. Okay, so the last section in this chapter is thermodynamics and kinetics. Okay, don't worry, it's not going to be a whole bunch of equations here. But I wanted to tell you the difference because reactions in organic chemistry aren't mysterious. There's a reason for something to do something. Okay, so two of the major driving forces are thermodynamics, meaning you're making something more or less stable, and kinetics. And kinetics is different because you can make something less stable but faster. So thermodynamics is all about the energy of the reactants and the products. Okay, we're going to have these really cool little energy diagrams that show you where the reactants and products started and stopped. But kinetics is all about how fast the reaction went. Okay, so if it's how fast the reaction goes, you can start with something that has this amount of energy, and if it goes really fast, you can end up with something with a lot of energy. That's not thermodynamic. That's going the wrong way. So we're going to see how they do it. So what we have to do is think about how to apply the thermodynamic and the kinetic product to our reactions. And so in the case of our system here, the equilibrium should favor the products if the reaction is going to go forward, right? Meaning it's thermodynamically controlled. It's controlled by energy. You're looking at the reaction progressing through that, okay? Now, but the reaction, the forward reaction, has to be faster than the back reaction, or the equilibrium will shift back the other way. So the reaction rate to form your products has to be fairly quick and has to be faster than the competing back reaction. Okay, do we see the difference between thermodynamics and kinetics? Okay. So when we have this, we have kind of an equilibrium constant. Remember, we had those acid constants, but we're going to have equilibrium constants as well. And so we have a reaction of A plus B is going to maybe go, maybe not, go to products C. Sorry. Go to products C and D. Okay, so to get our equilibrium constant, we're going to do exactly what we did with the acid-base reaction. Our equilibrium constant is going to be equal to the products, the concentration of C times the concentration of D, divided by the concentration of the starting materials. This is the same kind of equation we did for those acidity constants, right? So when we do that, we can say that this will give us, just by measuring the concentrations of the products versus the starting material, we get that equilibrium constant. Now, there's a principle called Le Chatelier, which I can't do French very well, so Le Chatelier, that says that you can play with this equilibrium constant. by adding or subtracting one of the components. So let's say you had your equilibrium constant, your reaction got to an equilibrium, and you had, 100 parts A and 100 parts B, okay? And you want to change that equilibrium. All you have to do is either add more A or add more B, and that's going to shift the equation, okay? So that means that we can change the equilibrium by adding more or less things. So what if we wanted to, these were our starting materials, right? And these are our products. And let's say it went halfway. But one of our products here, D, is water. So we could remove water from the reaction to drive it further to products. Okay, that's what Le Chatelier's principle means, is that we can drive the equilibrium by changing the starting materials or the products. And in this case right here, if we pull off water, we're going to end up getting all the way to our component C. It's all going to go to our final product. All right, question.
So moving product favors more of the product?
Removing, disrupting the equilibrium in any way will do it. But in the case of this, if the back reaction with water is what's keeping it from going forward to completion, by removing the water, it's removing it from the equation and therefore letting you drive to your product C instead. So it's perturbing your equilibrium by removing one of the components that's not letting you go forward. Okay. So you can also do it by boiling stuff off, or if it precipitates out a solution. It's no longer participating in the equilibrium. If it's no longer participating in the equilibrium, it can be driven to products better. All right. So how is a reaction gonna go? How do we know? All right, so if our equilibrium constant is greater than 1, products over reactants greater than 1, that means the equilibrium favors products because there's more product than the starting material. And that means that the equilibrium typically will lie to the product side or the right side of the equation. And these tend to be useful reactions. The reaction thermodynamically and by equilibrium will move to the products we're hoping to have. Okay. But what if the equilibrium constant's not above 1? That means your starting materials are in greater concentration than your products. Okay, so that means that the starting materials are favored. If the starting materials are favored, the reaction does not want to progress and therefore is not a useful reaction for us. Okay, so that's why the equilibrium constant is so important. So all of the reactions that are useful to us, we're going to have an equilibrium constant greater than 1 because it favors products. All right, and all the ones that are less than 1 are not going to be favorable for us at all. So let me talk about this last little thing right here, and it's called the Gibbs free energy. We can also equate it to enthalpy, and what we're looking for in the Gibbs free energy thing, which is this delta G0, delta G signal, is the change in energy between the starting materials and the product. So that's the delta G, the change in energy from the starting materials to the product. Okay, so if we were to do an equation of that, it would be simple. It'd be the change in free energy, Gibbs free energy, is equal to the energy of the products minus the energy of the reactants. Okay, so that's the difference. Now, if this is positive, that means the products had more energy than the reactants, right? Because your reactants here are being subtracted from it. So if your overall energy is positive, the reaction favors products. So what does that look like? Well, that means that if we go from this energy here, which let's call those the reactants, and then we'll go to this energy here, and we're going to call that the products. So the difference in energy between the reactants down here, reactants, and the products here, the reactants have less, the reactants have less energy than the products, because that's, increasing energy scale here. Yeah.
So if energy had to be put into the reactants, wouldn't that be unfavorable? It takes more things to.
Hold on, sir. So in this case here, the reactants are lower in energy than the products. So what is our delta G? Positive or negative? It's negative. So that means we had to put a whole bunch of energy into this reaction to get to the products. And so is it thermodynamically favored? No, because the products have more energy in them than the reactants did. So let's do it the other way, where we have our Gibbs free energy of our reactants here, and then our Gibbs free energy of our products. So our reactants are going to lose energy when they get to products. Our products are more stable. Our Gibbs free energy is positive, and this reaction favors products. All right, so that's what we're talking about with the Gibbs free energy. By comparing the Gibbs free energy of the starting materials and the products, you tell whether the reaction is favorable or not. When the Gibbs free energy change is positive, it's a favorable reaction. When the Gibbs free energy is negative, it is a non-favored reaction. Okay, so questions on that? So we can actually take this energy and relate it to the equilibrium constant. I mean, that's why we wanted to measure the equilibrium constant, right? Turns out that the delta G is equal to a constant, which is minus 2,303 times that constant times the temperature log Ke cubed. Okay. It's not Planck's constant, it's the gas law constant. So that means that if we have an equilibrium constant that is negative, when we do our calculation, you're going to end up with a delta. But the important thing here is that the equilibrium constant and temperature are important for that delta free energy. Okay. So again, if we think about the equilibrium constant here, the log of our equilibrium constant, if it's positive, if the log of just this equilibrium constant is positive, we're going to end up with a negative sign here. Meaning that you have a negative Gibbs free energy, and it means energy is released. Released. Okay. And if energy is released, the equilibrium will favor products. You're giving away energy to make something more stable. Okay. If the log of the equilibrium constant is negative, we're going to have a negative here and a negative here. You're ending up with a positive Gibbs free energy. And that means energy was absorbed, because the products have more energy than the starting materials. So it's not a favored reaction anymore. Okay. And in this case, if that log of the equilibrium constant is negative, it favors starting materials. I'm sorry. Yeah, favorite starting points. Okay. Okay, so it's a cute little equation, but it helps us understand that the equilibrium constant is directly related to the energy of the reaction. Okay, so the other thing that's related to the energy of the reaction is the entropy. And there's actually an equation that we can use that takes entropy, enthalpy, Gibbs free energy, and ties them all together. But I want to talk about entropy first. Entropy is important, especially in higher temperature reactions, but what does it mean? Well, a change in entropy is disorder. So if you're having a increased disorder, you're creating more molecules. So you're going from one molecule and breaking it into two molecules, that's more disorder. So a positive change in entropy is going from one thing to more. So that will increase entropy. So that entropy, you can see in the previous reaction, we had A plus B going to C plus D. Is there a change in entropy in that reaction? No, because we're going from two things to two things. So there's no change in entropy. But if we take two things and combine them, we go from two things to one thing. What has happened to the entropy? It's decreasing because you've gone from two things to be disordered to one thing being disordered. Therefore, it decreases the entropy. Okay, so how does that really affect us? Well, it really affects us when the temperatures get high. Because if you think about higher temperatures, you have molecules that are moving around faster. That's more entropy. So there's a temperature component associated with that entropy. Okay. So I said that there's a way to relate entropy, temperature, and Gibbs free energy. Okay. So this is the equation that is most important. And it's the delta G is equal to delta H. What's delta H? Enthalpy. Enthalpy. It's basically the change in heat. Delta G is the change in free energy. Delta H is the enthalpy, the change in the bonding energies, minus temperature times delta S. Okay, so let's think about this. At room temperature, delta T is not going to be very big. If we're not changing entropy, this minus T delta S kind of goes away, which means the bond energy, delta H, enthalpy, is approximately the same as the Gibbs free energy. This only matters when T starts getting really high or you start breaking a molecule into 2 or 10 or 20 pieces, enthalpy becomes an issue. But most of the time, we can equate the free energy to the enthalpy, which is the energy held within the bonds. Okay. So that means that we have an approximation until temperature usually gets above 500 degrees. We can usually just leave that enthalpy term out. Okay, so what does this say? It says that delta G is approximately delta H, and the total change in energy, in that free energy, can be measured by measuring the energy actually in the bonds and comparing the products to your starting materials. So that's where we're going to get the calculation for Gibbs free energy is actually been measuring the bond energies in the different bonds we have. So we're going to compare the total, all the different bonds in the products, to all the different bonds in the starting materials, and see which one's positive or negative. Okay. So the only time you'll ever have to worry about entropy is when you are going to dramatically change the disorder, like going from one thing to 5 things. Or when you go from one thing, or for 5 things down to 1 thing. Okay, so let's look at this. So if we had something that breaks apart, that increases entropy because it created more things. Okay, but what if we had something, instead of breaking this apart, what if we took this end and added it to that end? We still have 1 thing, so we didn't have a change in entropy. We've just done a reaction, but we didn't change it. So most of the times when we're talking about this entropy thing, that if your products are more disordered, more parts, or more fragments, etc., it will favor the product. If entropy is fewer things, then it will favor the. Okay, and so really the big thing about thermodynamics and kinetics is thermodynamics is all about the energy in the comparison between the reactants and the products. And we will measure that typically using our delta H. Delta H and delta G are approximately equivalent unless we have entropy as a major contributing factor. All right, questions on that? Okay. Yes. We're gonna apply the concept to show you why certain bonds form other bonds because of their energy. And we're gonna have we're gonna actually draw diagrams called energy diagrams. And so the change is gonna be most important. We are not going to calculate out enthalpies or anything like that. Okay, so I have 15 to 20 minutes. So let's start chapter 4. Okay, this is the last chapter before our exam. I'm going to get through all of chapter 4 today. No. By Wednesday, and then we'll have some time for review for the exam on Monday, the 21st. Monday, the 21st is when the exam will be. So we'll have all of that. We'll have a little bit of time for review Wednesday afternoon. So look for that. If I somehow don't have a lot of time for that, what I will do is I have a review video I'll put on YouTube. So look for the review video on YouTube if we don't have enough time on this. Okay, so now what we've done is we've learned about energies and bonds and acidities and stuff like that. Now let's talk about naming our basic hydrocarbons and some of our groups, because in chapter 2 we learned a bunch of functional groups and not really exactly how to name them. So we're going to learn our systematic approach to naming our, anybody not log in? Okay. All right. So what we're going to do is we're going to come up with a systematic plan on how to name everything. Okay. And what we're going to start with is that we're going to start with about 5 basic rules. And we're just going to keep adding to those rules. So you're always going to start in the same place. It's just eventually you're going to have a different functional group that you'll have to start figuring out where things go. Okay. So we want to do this in a systematic way. And we call this the IUPAC system, which is the International Union of Pure and Applied Chemistry. Okay. We're going to use their thing for most of our names. I will be sharing common names that you'll have, but the best way to name something is going to be using the IUPAC rules. Okay, so before we start, I want to say that things that are substituents are a functional group attached to something else. Now we saw in chapter 2, functional groups could be a lot of different things. Okay? And so we want to make sure that we keep those in mind. The substituent is attached to the bigger molecule. Okay. Now, there will be several common names that we'll use, and I'll show you those when we get there. Okay, so the first thing we want to talk about is there's 4 parts to every name. There's the substituents. That's the first part. Then we have what's called the prefix, the infix, and the suffix. The suffix is your functional group. Well, let's go one suffix. Let's talk about suffix. Suffix is the last part of the word. So we have our prefix, our suffix, and our substituent. In the case of alkanes, there are no functional groups. The CH is our only functional group. So we have denoted that in our last part of the name. The suffix tells you which functional group is present. If you have nothing but carbon hydrogens, then we have it in ANE. So that's our first functional group is an alkane, ANE, alkane. Okay, but what are all the other parts? Okay, well, if there's nothing else attached to it, we're going to try to find our longest carbon chain and assign that by the number of carbons in it. And we're going to do that using this system here. 1 carbon is meth, 2 carbons is F, 3 carbons is prop, 4 carbons is but. So you probably want to be able to know all these, if you don't already. The first 4 are the hard ones. Everything else kind of goes easily until you get to icosane, which is 20. Okay. So if we look at this word right here for the meth portion here, is telling you how many carbons are in the chain. The ane part here is telling you only have carbon hydrogen and you only have carbon-carbon single bonds. So even in something as small as methane, we have 2 pieces of information given to us: number of carbons and the nature of those carbon-hydrogen bonds. Okay, so that's the first thing we want to do. But in the case of a substituent, we want to change the name slightly to show that it's a substituent. Let's say we have a small carbon chain hooked to another carbon chain. We want to demonstrate it as a substituent by naming the number of carbons in that chain. But instead of having A and E, we want to do YL. YL is telling us we have X number of carbons as a substituent. So in the case of meth, we're no longer methane, but we now have the methyl group, and so it'd be a methyl substituent. So you know there's exactly 1 carbon on branching off from that main chain, or the longest chain. And we do that for the other ones too. So we have meth, F, and prop, and but, and these are all things you'll need to remember. Notice they all have symbols too associated with them. Me stands for methyl. You can have that hanging off a chain. ET for ethyl, PR for propyl, and BU for butyl. Okay. So most of the time when I draw them, I'm going to show you in stick form here. Okay, what's this little squiggle on the side here? That's the bigger chain that it's attached to. Okay, the little squiggle showing you it's a substituent. So it's on something bigger. Okay. Now, once we get up to propyl and butyl, there's isomers possible. So the first isomer we're going to talk about is the propane. It's isomer because we have a total of 3 carbons, but we can hook it to the end carbon or the middle carbon. So in that case, we have 2 different isomers, where if we drew it out, notice it's on this first carbon here. And on this one, it's on the second carbon. And you say, well, what if you do it over here? Well, then it's the same. It's just the other side of the molecule. So we have 2 different isomers possible here. And so when we have it at the end of the chain, we call that the normal. It's usually denoted as an N, a little teeny N. It just means you don't have an isomer, it's just a straight chain. But if you do have it, you have an isomer, and this one is called isopropyl. So you have an isomer, isopropyl. And I like to call it, this is the bunny ears, is the isopropyl, and then we have it on the substituent. So these are 2 isomers you'll need to know. Ethyl doesn't have one, methyl doesn't have one, only propyl, and it only has 2. What if we add 1 more carbon? We get to butyl, right? Well, we have more isomers available to us. in butyl. So the first one is the simple one, which we call N-butyl, little n meaning normal or straight chain. But if we have bunny ears, but we still have a total of 4 carbons, we call it isobutyl. So it's an isomer of the butyl, but it still has the 2 bunny ears that you see in isopropyl. What if you instead had this structure here, again, still attached to one of the carbons near the end? What if we attached it to the second carbon in the chain? If we attach to the second carbon in the chain, we call that sec-butyl, or secondary butyl. Okay, and oh gosh, if we rearrange it again, and now we still have 4 carbons here, and we hook it to the one in the middle, what is that carbon? Is that a primary, secondary, or tertiary carbon? It's got 3 methyl groups on it, so it's going to be tert-butyl, tertiary. So our isomers are iso, sec, and p-butyl. All right, questions on that? And again, the stick drawings here are the ones we're going to most likely use in class. Yes?
You count like the sec-butyl, second carbon, you're counting from the right to the left.
Well, it's a secondary carbon, but yes.
Oh, secondary
It's
carbon.
secondary carbon. See right here, we have 1 carbon on each side. Here, this would technically be a primary carbon on the end here until you attach it to that. So the secondary carbon, and then tertiary carbon before it's attached to the chain. That's one way to remember it. Okay. Okay. Then there's the weird one, which is a derivative of the 5, and it's called Neopentyl. Neo meaning new, pentyl meaning 5. So it's the new pentyl. And it's sometimes used, but notice it has this portion here would have been tert-butyl. It has 1 more CH2 on it. So it goes from 4 carbons to 5 carbons, and we call that the neopentyl. That's the last of the common substituent names you'll need to know. So ethyl methyl, 2 propyls, 4 butyls, and the 1 neopentyl. Okay. So that being said, okay, so let's figure out all the components of the name. So the first part of the thing is the parent chain. That's going to be denoted by the number of carbons in its longest chain. So we're going to use that meth, F, but, whatever, icosane. That's going to tell us how many carbons are in that main chain. The next thing we're going to see is the suffix, which is that end part, tells us what functional group's there. Okay? So we have the parent name, which is the number of carbons in the longest chain. We have the suffix, the ANE right now, ANE. And then the prefix tells you where all of the different things attached to it are. Whether it be an alkyl chain or some other group, the prefix is going to tell you where it is. Not only what it is, but where it is by telling you a number somewhere on that parent chain. Okay, so if we are to think about it that way, we can derive any group. So in this case here, we, again, separate our long chain alkanes, our parent chain, from our substituent by using that YL, okay? So if it has a YL on it, that means that group of atoms is not the main chain. It's a substituent on the main chain. So then we have to go to the main chain is whatever the longest set of carbons is. And let's put a little isopropyl down here. So that isopropyl group is a substituent on this main chain. And we're going to number that main chain by the number of carbons in that main chain, not including the substituent. Okay, so let's apply this and see how well we can do. Okay, So the first thing we need to do is we need to find the longest chain. But you have to actually look at it a couple of times because the longest chain is not necessarily the one in the straight line. So we need to pay attention to this. So in this case here, we can start from somewhere and just go 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would give us 9. But I don't think that's the longest chain. You? Okay. So if we go and say, okay, well, maybe that long one that's going up and down is the one. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That might be the longest chain, but we got to make sure. 1, 2, 3, 4, 5, 6, 7. So that would be shorter. 7, 8, 9, 10, 11, 12. So that would be a 12 as well. So that might be a long chain. So we need to find whichever one's the longest. That is now our parent hydrocarbon. And in this case here, we have 12 carbons. So what's our parent name? Dodecane. Cool. And now we have substituents on there, and those substituents will have the eel sounds on them. Okay, so again, pay attention to the longest chain will not always be the straight line. Sometimes they'll even turn around and go in a loop. So just pay attention to that. Okay. So now, next rule. So that's the first rule. Find the longest chain. Everything else is a substituent. The next thing we have to do is if you have a choice between two chains of the longest chain, like I said, you had two different ways of going to get 12 carbons here. You need to do the one with the greatest number of substituents. So if you have a choice between 2 substituents and 3 substituents, depending on how you count, you want the one with 3 substituents. Okay. So let's look at that on here. So instead of on this one right here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So if we numbered it in this direction here, we get 13. If we numbered it in this direction, we get 13. So 13 is our number. We just have to figure out what our substituents are. So in this case here, if we number it along this chain here, we'll end up with 1, 2, 3 substituents. Okay, let's see about the other one. If we numbered it along that axis there, we also have 1, 2, 3 substituents. So that means that, oh, those are the same compound. So we just want to be able to do it so we have the highest number of substituents. And now we can start locating our substituents because we know where they are. Okay, so let's locate our substituents. So we wanted to find our longest chain, and we haven't decided which side to number it yet. But the way we want to number it is so we want the, if you only have one substituent, it needs to be on the lowest number possible. Okay. If you have more than one substituent, you want to have the lowest numbers possible. Okay. So let's look at this example here. We have a total of 8 carbons in our main chain here. And we know that's our main chain because that gives us a total of 3 substituents. Okay. But we have to figure out which side to number from. Okay. So if we numbered from, let's start with, if we numbered from right to left, right here, the numbers would be on the top here, 1, 2, 3, 4, 5. Where's our first substituent? Is on the 4 position, and then our next one's on 5, and the next one's on 7. Okay. But if we number it from left to right, our first substituent's on the number 2. Our second substituent's on the number 4, and our third substituent's on the number 5. So those are lower numbers of placements for the substitution. So we want to make sure that we do that So we go for the lowest number possible. All right, I will come back to this on Wednesday and we will continue. I'm gonna stop sharing. I'm gonna stop recording.